govern our universe as a result of the process of cosmological natural selection. Rewrote quantum gravity, which came out in 2001, The Trouble with Physics, 2006, and now Time Reborn, From the Crisis in Physics to the Future of the Universe. As its title suggests, this is a highly ambitious and important book, which takes as its thesis the startling proposition that time and its passing, which, far from being an illusion, as sages and more recently physicists have suggested, is in fact fundamental and real. And accepting this reality can provide us with a new way of understanding why the fundamental laws of the universe are as they are. Professor Lee.
To present this book and the thought that went with it. I also want to get a sense of who the audience is. So how many of you are physicists? Wow, okay. And philosophers? And someone likes both? Okay. But of those who are physicists, well, this is a talk designed for somewhere between students and the general public. So there are many cases in which there are more rigorous ways to say some of the things I'll be saying. And if anybody wants the more rigorous version, then you can come on Thursday, I think at 4:30 to the philosophy department, where I'll be giving the philosophical version of the talk. But please object here. I'll be very interested to take questions afterwards. And if somebody really is dying to interrupt me to ask something, then that's fine too. So that's the cover. Okay, that's the American cover. This book is part of a project which has been going on for 7 years with the philosopher Roberto Ramírez at Harvard Law School. And there is another book in preparation which is a more rigorous formulation of the arguments written by Roberto and myself. And again, if you're interested in that, that will be forthcoming. Now, my subject is time, and science began with time. And Anaximander, who my friend Paul Ravelli says is the first scientist, had this to say: this is the only full fact that we have. All things originate from one another and vanish into one another according to necessity, in conformity with the order of time. So time was on the minds and was central to the thinking of the first scientists. By now, physics has proceeded to dismiss time. Julian Barber, who works here at Oxford and lives nearby, had a famous book, The End of Time, about a decade ago, in which he's argued that the fundamental laws of quantum cosmology, that is when you apply quantum mechanics in a cosmological context, don't have time in it at all, even as a variable in the equation. There's no functions of time that play any role. But long before that, time in the sense of the present moment, in the sense of our experiences of the flow of time, have been, I hear some noise. Is that?
I think it's your jacket to get to the microphone.
This jacket over here. Okay, is that better? Okay. Time in the sense of the experience of the present moment, the experience of the flow of time, and in the sense of there being an objective distinction between the past, the present, and the future, have been eliminated from physics. This is a famous letter that Einstein wrote to the widow of a friend of his who had just died. People like us who believe in physics know that the distinction between the past, present, and the future is only a stubbornly persistent illusion. As my introducer said, this book is an argument to restore time to a central place in physics and in science. Now, one way, there are several ways into the argument. Here's one way into the argument. I want to begin by talking about the philosophy of naturalism. Philosophy of naturalism is the idea that everything that exists is part of the physical, natural world that science studies. There are, if you're a naturalist, there are no other worlds, there's no world of mental events separate from their relationship to physical events. There's no worlds of angels. There's no, and this is controversial, there's no separate platonic realm of mathematical objects. There's just simply the natural world. The way I want to structure the argument is that naturalism has been hijacked by kind of mysticism about mathematics. And I'm going to explain briefly, and do so in more detail in the book, how it is that this hijacking took place. So that by now, if you're a naturalist, you're very likely not to believe that all that exists is the world that we perceive and experience. You're very likely to believe that all of that is an illusion, as Einstein said on the previous slide, and that what really exists is some timeless mathematical equation or mathematical object, which is the true existence of the world, and our perceptions of it are just somehow illusions. So I call that hijacked version of naturalism version 1. It comes from the atomists, this idea that the world consists of nothing but, as I think Lucretius said, atoms moving in the void. To spell that out a little better, atoms, eternal and unchanging with whatever properties they have, eternally given, moving in the void according to timeless laws, which govern the motion and the interaction of the atoms and are also unchanging, in an empty space in the void that never changes. Now this has to be updated a little bit for general relativity. The void turns out to change too, but that's only a point of detail. So let's start with that image of atoms moving in the void. All else is secondary, what John Locke calls secondary qualities in all of our experiences. You could say emergent or secondary, depending on what community you speak in. Not part of the fundamental description of nature. The fundamental description of nature, when you break things down, is just atoms moving in a void. Now let me separate this postulate from two things which are obviously true. There obviously are atoms. We know very well. I'm not questioning that. Nothing that I have to do in this talk or the book questions the usual practice of physical science up to this point. There obviously are atoms. What's in question is whether all the properties of things that exist in nature are the properties of atoms that science describes, like masses and charges. They're obviously moving according to very general laws. And it's obvious and true that the method of reductionism is very powerful. Reductionism says when you have something you want to understand which is made of parts, it's good advice to understand the dynamics of those parts and how they interact with each other to cause emergent properties in the whole. That's good advice, but it's self-limiting. And part of my message is that naturalism version 1 is self-limiting. One way in which reductionism is self-limiting is what happens when you get to the properties of the things which are the smallest things. So let's assume that the elementary particles described by the standard model of particle physics are really fundamental. They don't have parts. If they do, this is what I'm about to say will apply to the parts. They still have properties. They interact with certain specified interactions. They have charges that describe the strengths of those interactions and their participation in them. They have masses. Where do those properties come from? Well, reductionism will no longer work because they have no parts to break them down to. Now, the laws by which the atoms move are expressed by mathematical formulas. And there are two stories about this, a heroic story and a pragmatic story. Roughly speaking, what I think has hijacked naturalism is the heroic story. The heroic story is the world is really mathematical, fundamentally mathematical, and what we physicists have done is discover a way to transcend from ordinary reality to this transcendent mathematical reality, which is timelessly true. We are a sort of priesthood, because it is a religious calling, that way of putting it. That's the heroic story of why. And we have discovered those equations, but they've been there all along. They are the timeless truths of nature. The pragmatic story is that in physics we observe things like chalk flying through the air. We make observations of where the chalk is, when it is. We use rulers and clocks. Those are numbers. We discover patterns in those numbers, that is in the records of observations. Those patterns sit in the records of observations. Once taken, they don't evolve, they don't change, because they're records. That means they don't change. Okay? And those patterns amongst numbers are representable often by mathematical formulas, because that's what mathematical formulas do, is they represent patterns amongst numbers. So there's nothing deep or metaphysical about the use of mathematics in codifying results of observations. It's interesting that the mathematics is often very simple and very beautiful, and that's something I can come back to later. But it doesn't mean that mathematics is a description of reality. Now, here's one way to say more precisely what we mean by mathematics governing the description of the world. We talk about the state of the system, and we talk about how it evolves in time. The state is gotten in ordinary mechanics by measuring the positions and the motions of all the atoms at a given time. We can call that now. That's just the name of some mathematical list of numbers and that gives the state of the world now. There's another formula that gives the state of the world at some future time, which we can call future. And a law is a mathematical transformation that acts on the state now to give the state in the future. And that will be good enough for the purposes that I want to critique. It's analogous to, or it can be emulated by a computer program. So now is the input to the program, the laws is the program, which runs and gives output, which is the evolution at a future time. And it's very interesting to think that what's going on here is that we're making a model in which time, somehow acting in the real world in time as we experience it, bringing about changes in the world, is being emulated by a computer program, or equivalently by a mathematical formula. And of course, there are mathematical formulas that are not emulable on computers, but it's a point of detail I don't need. Okay. And a computer program encompasses logical relationships which hold timelessly. So the action of whatever is really causing change in the world is being emulated by something which is embedded in logic, which is timeless. And that, if you like, is part of the way in which I think that we all fooled ourselves into thinking that reality is timeless. Time is emulated by computation, which means in a sense that time is not fundamental, because if the progress of causal actions in time can be emulated by a computation, then it means that they are mirrored in logic, which is timeless, and therefore time is not essential. Time, in the sense that we experience a flow of time acting causally to cause future moments and present moments, is not necessary for the description of nature. Another aspect of this, of course, is that the belief that, at least in classical mechanics, or at the level of quantum mechanical states, the future state is completely determined from the present state. It's another implication of naturalism number one. So if fundamentally an implication of that is that nothing happens in the world, it's not explicable in terms of the motion of atoms according to laws, and therefore nothing ever really new happens. Anytime you think that there's something new, it can be reduced through the method of reductionism to just another configuration of the atoms. And there's a whole set of implications of this that I don't explore in this talk, for example, having to do with free will, philosophy of mind, and so forth, which I'm not done thinking through and not really able to address, but I'm going to raise them in an interesting way. Okay, now, just to rub it in, Thomas Sima is a character in the play Arcadia by Tom Stoppard. And she is a very precocious young student, and she expresses the idea here. If you could stop every atom in its position and direction, and if your mind can comprehend all the actions thus suspended, then if you were really, really, really good at math, you could write the formula for all the future. And here's what Tom Stoppard shows is clever. And although nobody can be so clever as to do it, that formula must exist just as if you could. That's naturalism version 1. If she were a modern character, she would say, rather than being really good at math, you had a really good computer and were a really good programmer, and then you could write the program which would contain as output, give as output the future. And again, although nobody can be so clever as to do so, that program must exist in a sense, as if one could. This is again the metaphor of the universe as a machine, whether as a clockwork several centuries ago, when those were the machines they were most proud of, or a computer half a century ago, when those were the machines they were most proud of, these days is a quantum computer, as for example, Seth Floyd will speculate that the world is a quantum computer. I said this already, I apologize, but it's important just to rub it in. If the universe evolving in time can be emulated by a piece of mathematics or logic simulated on a computer, then time is an essential. That's naturalism number 1. Now, some people go even further than this, not just that the universe is emulatable by a piece of mathematics or logic, but that it really is just a piece of mathematics. That is all that really exists is mathematics. And one person who makes this hypothesis, which he calls the mathematical universe hypothesis, is Max Tegmark. The universe simply is the mathematical formula that is its truest representation. And here the assumption is that there is some mathematical object which is isomorphic to the universe in the sense that every true property that a scientist could investigate, and if you're a naturalist, those are all the true properties of the world, must be mirrored by some provable property of that mathematical object. And then this hypothesis says, not only is there a mirroring, but that's all that exists is this mathematical object. Now here's a bit of humor. Sabina Hassenfelder is a physicist. She's a professor at Norditon, Stockholm, and a blogger, and this appeared on her blog a while back. Max Tegmark says the whole universe is a mathematical structure, so he must believe he is a mathematical structure. And I must be a mathematical structure too. I wonder what it feels like being a mathematical structure. Now that's the key question. Because we all experience being in time, experiencing everything we experience and think in a moment of time, which is one of the flow of moments which we remember and discern. But there are no moments, there are no present moments in mathematical structures. Mathematical structure is simply our set of logical relations which hold, once defined, which simply hold whenever they can be verified or defined. There might be a function which you could write as a function of one variable, f of t, and call that a function of time. But t is the reading of a clock. That doesn't mean that the mathematical object is changing in the sense that we experience the world changing. So what does it feel like being a mathematical structure? Before I go on, I'm going to come back in a minute and emphasize that point. Okay. If the world is isomorphic to a mathematical structure, and mathematical structures have nothing that coincides with present moments or their sequencing or flows, then those must be illusions. On the other hand, if they're not illusions, if your version of naturalism says, I experience the world through moments of time, and that's a fact about the world which must be part of nature and incorporated in my naturalist view of nature, then there is no perfect mathematical mirroring of the world, because here's a thing that's true of nature, which is not true of any mathematical object, which is it exists always in moments. So that's what's at stake here. Now, another related issue is this idea that time is another dimension. And I found this quote in a review of my book that I was very glad for by James Glick. I didn't know of it. H.G. Wells, writing some years before Einstein, and Minkowski and so forth, there is no difference between time and any of the three dimensions of space except that our consciousness moves along it. Of course, except is a kind of small exception, but the idea is around that time is another dimension of space. Einstein gave us reason, and this is not part of the talk because this is a more public version of the talk, but if people want to ask me about it later, I will address relativity theory and the mixing of space and time and relativity theory. But Einstein, through the relativity of simultaneity and the mixing of space and time, gave us further reason to think that time is just another dimension of space, which leads to this quotation, which is my second one, that the distinction between past, present, and future is just an illusion. But Einstein, even Einstein was ambivalent about that. And here's a quotation from the philosopher Rudolf Carnap in his memoirs. And I'll just read the red part. Clearly they were drinking one night and they had the kind of conversation that students, I'm sure, here at Oxford have all the time when they drink late at night. And thinking about science. Einstein said that the problem of the now worried him seriously. He explained that the experience of the now means something special for humans, something essentially different from the past and the future, but that this important distinction cannot occur within physics. Einstein thought, jumping down, that there's something essential about the now which is just outside the realm of science. By the way, that last sentence has two meanings in English because just is an ambiguous word. So I had a friend check the German original, and it's just in the sense of unavoidably, far from, not just in the sense of very near and almost. So Einstein was worried about what I was just speaking about, the loss of anything representing the fact that we experience the world through the present moment in sequence in the equations which represent the description of the universe in relativity theory. So this is where version 1 of naturalism ends up. In a world in which the experiencing of the present moment is an illusion and so are the distinctions between past, present, and future, in a world in which the future is determined from the present, in which what is real is the whole history of the universe laid out as one, so also our beliefs in free will, novelty, agency, imagination, values, all these things must also be illusions, because they're all things which are understood to arise from our situation of living in a moment, which is the present moment. So naturalism version 1 has been enormously powerful, and I have nothing to do to question its importance and its power. But it leads to a view of nature which is curiously alienating from human aspirations. And I think that this is worth taking seriously. I think that this is part of what Einstein was worried about. What we care about as human beings all stems to our experience of living in the moment. What we believe are our capabilities, our possibilities, our agency, are all part and extensions of the fact that we live time moment to moment. If that's an illusion, then where does that put human values? Where does that put the humanities? And no wonder there are people who hate science, who hate physics, because the view of science that we've developed of the universe is alienating. It was summed up in Steve Weinberg in the first few minutes. The more we know about the universe, the more pointless it seems to be. Now, this is what's at stake with the adequacy of naturalism version 1. I'm not here to attack it on those grounds. I'm not coming as a humanist or a politician or a poet to talk about the limitations of naturalism version 1 as an inspiration to my human work. I am coming as a scientist to talk about the limitations and the incompleteness of this view of the world. Because I claim A, it's incomplete, and B, it's self-limiting, and see when taken too far, it's contradictory, it's fallacious. So let me go through these one at a time. First, it's incomplete. Okay. Naturalism is supposed to be about everything that is part of nature. If you have an adequate naturalist view of the world, then you include everything we know about the science studies that we're aware of. But certainly we're aware of the fact that we are conscious of time. We're aware of the fact that everything we experience is experienced in the moment of time. And if that is not adequately explained in a theoretical framework, it's not an adequate theoretical framework if we aim to describe everything in the world. Now here there's a crucial distinction which let me introduce and now I'm going to be highlighting in the next 5 or 6 slides. As a method, naturalism version 1, as a method for studying parts of the universe, which is what we actually apply physics to so far, it's perfectly adequate. When we do an experiment in the laboratory, whether in a building on this campus, at the LAC in Geneva, we're talking about a specified finite domain of space and time, outside of which are the observers, outside of which are the experimental devices, outside of which are the clocks that we use to record when things happen. And that is perfectly adequate. It's perfectly fine to use the idea that we have a set of states of the system that they evolve in time according to a mathematical equation. That's perfectly adequate. It's only when you raise your ambitious level, your level of ambition, and say, this method gives me a description of the whole universe, that you get in trouble. So that's where I want to take my argument, take my fight, if you like. With the extension of this method of science and this philosophy, naturalism version 1, from a theory of small subsystems of the universe to a theory of the whole universe. Now, I've already given the argument on this slide, so let me just highlight it. If we think that the fact that we experience the world as a series of present moments is part of nature, then this version of naturalism is incomplete. If we think this version of naturalism is complete in any of the versions, whether the world is just describable by mathematical equations which describe timeless laws, or the full-blown version in which the world is nothing but a mathematical object, okay, then our experience of time is an illusion, as is the distinction between past, present, and future. That's the incompleteness. But it's also self-limiting and fails on scientific grounds. And this is the key point, so I'll just repeat it. Where I think the key issue is the extension of physics from a method for describing part of the world to a method to describe the whole universe. When we, and I mean myself as well as my colleagues in physics, without analyzing what we're doing, just simply take the structure of physical laws and the assumption about the nature of physical laws that we have been using and have proven so successful up till now and apply them to cosmology, to the universe as a whole, we're making a mistake. And I want to detail the reasons why that's a mistake. That'll be most of the rest of the talk. Then, what I'll describe more briefly is some first tries in naturalism version 2, which is a version of naturalism that doesn't make that mistake. Okay. Again, the main fallacy is taking a method good for studying parts of the universe and applying it to the whole universe. One way to talk in a popular level about where naturalism version 1 works is what I call doing physics in a box. Doing physics in a box is what Thomasima was thinking about. It's the method where you take a system, say whatever is contained in this cup, you describe it by giving a description of all the possible states of the system, that is the positions of all the atoms in the air and all the molecules, and you have a space of states. If you're a quantum mechanical person, it's the Hilbert space, but otherwise if you're using classical mechanics, it's just a space in which every point is a possible configuration of the system, of the limited system we're studying, which can be ascertained by measurements made from the outside, ideally. Then, what is a law of nature? A law of nature is something that, given a state at one time, tells you how that state will evolve to future times. So formally, it gives you some curves on the space of states that never intersect each other. The way you use such a law is you say, my measurements show the present state is this. I evolve a certain amount of time measured by the distance along here, and that's my prediction for the state the system will be in. The space of states is given a priori and is timeless. Doesn't change as the system changes. The system doesn't add new states. And the law is fixed for all time. You don't change the law as you evolve. That's what I call popularly doing physics in a box. Also, another name for it is the Newtonian paradigm, because that was codified by Newton. Although historians of physics will tell me that I should really be going into a Gaussian paradigm. But, okay. The key question, can we put the whole universe in the box? Can we make a space of states that describes the whole universe, and a law which acts on the space of states that describes the whole universe, and claim that's a complete description of nature? That's what, by the way, we do in general relativity. So there's a well-worked out example of a hypothesis about what the space of states are. In that case, they're three-dimensional geometries. And what the evolution law is, in that case, the Einstein equations. So this has been developed quite a bit, and the critique has to apply to that case, which it does. There are several ways to tell that this method applied to the universe as a whole is self-limiting. One way is that there are major questions it doesn't answer. If you really think you have the cosmological theory, you should be able to answer Leibniz's call for sufficient reason, at least about big, obvious questions. And you can't. One of the questions that you can't address is not what are the laws, but why are these the laws, not other laws? It's not enough that physics is going to give a complete explanation of nature. It's not enough to say, what are the laws of nature? We know a lot about them. We may not have the complete unification, but we know a lot about them now. The standard model of particle physics plus general relativity, plus some adjustments of quantum mechanics to cover that extension to general relativity. But that's not good enough. If we really want to explain nature, we have to understand why these are the laws and not others. Why these initial conditions and not others? And to use this method, you have to give as input the present state, the so-called initial conditions, to get anything out of it by involving those initial conditions and final conditions. If you're a cosmologist, you think the initial conditions appeared shortly after the Big Bang, whatever that was. And we know enough about the universe to know that in our models there's a vast space of possible initial conditions, any point in the space, let's say, and the actual initial conditions near the Big Bang is in a very tiny corner. This is a point that Roger Penrose made in the late 70s very convincingly. The universe is so unusual in its early stages, is so symmetric, is so homogeneous, is so ordered, has such a low entropy compared to all those things to what it might if you took a typical state as the initial state, that is necessary to explain many features of the present world, including the very common feature that almost everything that happens in the present world is irreversible. So cosmologists have raised and have put focus on this question of why are the initial conditions so special? And within a method of science in which the initial conditions are input, that's not answerable. The method that takes initial conditions as input are self-limiting. You can't ask a computer program to explain its input, and you can't ask general relativity to explain what the initial conditions of the universe were. Those are not the only reasons the method of doing physics in a box fails when applied to the whole universe. The method that I've been talking about gets its correspondence to experiment from being very general. But at most, there's just one universe. I think there is one. And therefore, there's only one history in this scheme that explains our universe. What's the use of a general law on a cosmological scale? Laws have infinite number of solutions. Laws of the kind we're talking about have infinite number of solutions. General relativity in a cosmological setting has an infinite number of solutions. At most, one of which gives even an approximate description to nature. What about all the others? We have explained too little. We haven't explained the choice of the particular solution that governs nature. We've also explained too much because we've explained a lot of details of universes which don't exist. In fact, most of the theoretical power of the method goes to explain the details of universes that never exist. So there's a mismatch, and this mismatch comes because you're taking a method that's meant to apply to a very large number of cases, and applying it to a situation where there's one case. The method also requires a strict separation between its two inputs. The two inputs are what are the states and what are the laws. We can experimentally discern the difference because we can take a system and study it many times, starting it over and over again in different starting configurations, and therefore tease out which part of our explanation of the future is tied to the law and which part is tied to the initial conditions, to where you started. But if you only get one case, you can't tease it out. You have twice, in other words, usually you're making a hypothesis about what the laws are. At the LHC, you're making a hypothesis about what the laws are, and you test that in trillions of interactions. In the cosmic microwave background, you're making a hypothesis about what the laws were really in the universe, and a hypothesis about what the initial state was. And if you get an interesting result, it turns out, for example, there was a feature of the cosmic microwave background that was claimed to be seen a few years ago called non-Gaussianity. It doesn't matter what it is, and it's actually so far gone away. But it's a possible feature of the cosmic microwave background radiation. Within a week of that discovery, or claimed discovery, there are papers in the literature saying, oh, that's easy to explain by changing the laws that held the early times. The inflaton potential, if you want the technical term. You can just modify the inflaton potential and get that. Or you can change the initial state and get that. And since you only get to do the experiment once, the methodology fails to give you a clean test of either hypothesis. So I say there. So a lot goes wrong. This is just a summary. When we try to take the Newtonian method, the Newtonian paradigm, and apply it to the universe as a whole. And this is just listening to things that we've said. There's indeed a dilemma, which Roberto Unger and I call the cosmological dilemma. If you accept that physics so far describes subsystems of the universe, then you have to accept that physics so far is approximate. It's what we call effective. It's a well-defined language that the physicists here will know about. And if we talk about effective laws and effective theories, these are laws that hold approximately to a certain degree of precision within a certain specified domain of space and time and energy, and so forth. You might think that by expanding the domains of time and space, you make your theory more exact. If you don't expand it, you have to face the fact that you're dealing with an approximation, an approximate description of reality. But if you do put the whole universe within the domain that you're describing in your theoretical structure, you raise the questions that I've been raising, which can't be answered by the theory as we have it. So there's a dilemma, which we call the cosmological dilemma, which says that this method of science cannot give you a perfect explanation for everything we'd like to explain. It's self-limiting. Now, when you ignore the cosmological dilemma and just proceed, as I used to do and as many of my colleagues do, to apply theories of the kind that are well developed to the universe as a whole, you hit a bunch of fallacies. That's what we call the committing the cosmological fallacy. And you start to ask confused questions that are bandied about in the physics literature and the popular literature without answer, without progress towards. And these are some of them. What was the time before the Big Bang? What were the initial conditions for the universe? How are they chosen? What is the status of states and histories of the universe that never will be realized? How can you tell if an observed fact is a consequence on a cosmological scale of laws and initial conditions when you only get one? These are all churning of wheels that come because you've committed a fallacy. That's our claim. It's because you've taken a methodology which is naturalist one and applied it outside the domain where it makes any sense, where it is as empirical content. Okay? Hence, we need another methodology. And that is what I'm going to call naturalism 2. Before I describe naturalism 2, all the arguments given since the time of Descartes through to Julian Barber for time being eliminated as a part of the fundamental part of the description of nature are inessential if the method on which they're based cannot be extended to nature as a whole, to the universe as a whole. So also goes the argument that the future is determined from the present. It may still be true that the future is determined from the present, but not on the arguments that are usually given to it. Okay. Now, in the 15 minutes that I have left, I will introduce a sketch of naturalism 2, and it comes from going back to that disjunction, to that choice between believing that the world is isomorphic to a mathematical object and believing that our experiences of time, of the present moment, and of the flow of moments are real and should be included in any description of nature. And going back to that and taking the other fork, taking the view that time is real and hoping to explain things that naturalism version 1 can't have. So now, you know, in the kind of philosophy of mind, this is a very recent meeting. David Strawson, Thomas Nagel make an argument with regard to philosophy of mind that I think the structure of is interesting. So I make the same argument, this point. Surely what we know about the world includes the fact that we experience time as a sequence of present moments. Surely any naturalist must account for that. Naturalism version 1, which does not incorporate that, does not account for that, when taken out of its domain of validity, where it's perfectly good, becomes a kind of mysticism about mathematics. It ceases to be scientific, I would claim. What would a naturalism look like that doesn't make that mistake? Okay. So I start this new version of naturalism with the postulate of the reality of time. And by that, I mean the following. I mean something akin to what philosophers mean when they use the word presentism, although it's not completely identical to the usual versions. But here it is. All that is real in the present moment, which is one of a succession of moments. There are no timeless laws acting to cause evolution in time. Laws are part of the present state of the system. There is an objective distinction between the past, present, and future, and the laws of physics can refer to and rely on that distinction. And there is no mathematical object which is a timeless mirror of the whole history of the universe. That's what I mean by the reality of time. The future, the past was real, but is no longer so, but there are, of course, records and memories, and as Julian Barber calls them, time capsules of things that occurred in the past. The future does not yet exist, and therefore must be considered, at least until proven otherwise, at least partly open. Certainly given the phenomenon of quantum mechanics. that doesn't mean that we can't reasonably infer some predictions, because in the private domain, laws of nature are highly stable, as long as we're talking about much less than cosmological timescales. And we can learn a lot and predict a lot about the future. But the future may produce changes in laws and other phenomena which are genuinely novel and not predictable from their past. Nothing transcends time, not even the laws of nature. Now, that's the starting point. If we start there, we can try to solve the problems that naturalism version 1 can't solve. One of them is to explain the why these laws and why these initial conditions question. The present laws must have evolved in time so that they can be explained by the mechanism of evolution. We can take advantage of an observation that Charles Sanders first made in the 1890s, which I think is my next slide, so I'll go to it in a minute, that laws, if they are to be explained, must evolve in time if they are to have an explanation within science. By an explanation within science, I mean an explanation that has ramifications that imply new predictions by which the hypothesis can be checked. This requires that the Big Bang not be the first moment of time, that it be a so-called bounce to be replaced by some process or some phase transition, transitioning the universe from a previous era to the present era. Why do we know that? Because we know that out to redshifts of at least 5 or 6, there is no evidence that the laws of nature are evolving within the present side, within our universe. There is some disputed evidence for small changes of an Australian group of wet and others, but not definitively. And this means that time, as in causal change, causal processes which cause change, must be seen as prior to law, law being things that apply to generally to a large set of phenomena. So it has implications for our notions of time and notions of causality. This is a quotation of Charles Sanders Peirce, who anticipated the idea, but not the application of the idea. He just makes the point, really restating Leibniz's principle of sufficient reason, that it's not enough to explain what the laws of nature are. Law wants an explanation itself. Law is par excellence the thing that wants a reason for it. Now, the only possible way of accounting for the laws of nature and for uniformity in general is supposed the results of evolution. Roberto Unger, my collaborator on much of this, in the 1980s, and I won't read this whole quotation, but in a book on social theory, he had come to much the same conclusion about cosmology, not about social theory. Others have come to the same conclusion. So when I began to think this through, I discovered that this was not an original thought. It was just an unusual thought. Paul Dirac had speculated about laws changing in time, and the laws of nature changing in time. Richard Feynman, who we think about as the quintessence, pragmatic, unphilosophical physicist, in an interview with Fred Hoyle, I believe, filmed on BBC, speculated about that physics may join the other sciences in having necessarily historical component. I won't try to do this Brooklyn accent. But and of course, Johnny Wheeler had hypothesized that many universes are born from within black holes, so that what's on the back end or the prior end to the Big Bang singularity of an expanding universe is the collapse of a star to a black hole in some previous era of the universe. And he had called it reprocessing of the universe and speculated that when that happens, the laws of nature change. And there's some process governing their evolution. Now, since, for better or worse, I'm a physicist, I'm not trained as a philosopher, although I aspire to the quality of thought of philosophers. I certainly don't reach it. So as a physicist, when I see arguments like the ones I've been giving as guides, I don't think they definitively decide anything. I think they're guides to the invention of hypotheses about nature, and we investigate their validity by trying to make hypotheses which realize them. So having gotten myself to this point in the late 80s, I began to try to invent hypotheses about how the laws might have evolved in time. And one of them, which was the subject of my first book, Life of the Cosmos, was Cosmological natural selection. The other one, another one, there are several described in this book, it's called The Principle of Precedence. Now, I only have a bit more than 5 minutes, so I think I'll only describe one of them, which is the Principle of Precedence, because it's the newer one, and it's the crazier one by far. But let me just not go away without saying that Cosmological natural selection made 2 predictions published in 1992, which maybe somebody can ask me about in the discussion session, which have stood up to real tests. These are genuine predictions about things like the masses of neutron stars or the spectrum of cosmic microwave background fluctuations. And they have stood up to tests, including very recent tests, which proves the point not that the idea is right, but that by going from the idea of the laws of nature are timeless to the idea of the laws of nature evolve through some processes, and making hypotheses about those processes, we don't decrease the empirical content of science, which you might think by going away from holding on to this mythical timeless laws. You increase the empirical content of science by letting the laws evolve, because then the question of how they evolve becomes investigatable. So the principle of precedence. I'm going to use, since there are a lot of physicists here, I'm going to use the language of quantum mechanics, in which we prepare a system in some state, we evolve it by perturbing it, by influencing the outside atmosphere, the outside environment of the system, and then we perform a measurement on it. And when we do so, there's a set of possible outcomes. Quantum mechanics doesn't predict what the right outcome of such an experiment is, of preparation, evolution, and measurement, but it predicts a statistical distribution of possible outcomes. So in that context, if we set up such an experiment, we get some statistical distribution of outcomes. Supposing it was done in the laboratory this morning, our friend from the laboratory will report the statistical distribution of outcomes with some curve or some bar graph. This is probability. And this is something I won't say what it is, and there's some statistical distribution of outcomes. This is what they found this morning, but it turns out they did the experiment 50 years ago and found within errors, different people, the same distribution, and we're confident that if people do the experiment in the future, they will also find the same distribution, no matter whether it's next week, in a year, in a billion years, in 100 billion years. We expect the results of such experiments to be stable. Now, why is that? Well, we usually think that that's because the timeless law will act in the future as it is in the past. And the way that I put this is that my wording is important here. If we prepare and measure a quantum system we've studied many times in the past, the response will be as if the outcome were randomly chosen from the ensemble of past instances of that preparation. That is, if this is the statistical distribution, and we do it one more, we're going to get something which is likely to be within the peaks of the statistical distribution. And if we do it 50 times, we're likely to reproduce the statistical distribution. It's as if each time we're sampling from the past results. And why is that true? The common sense, the naturalism version 1 explanation, is that there's a timeless law and it acted in the past, it acted today, and it's going to act the same way in the future to get the same results. But that's a crazy idea. That's an idea fraught with metaphysical assumptions. Because what is this thing, a timeless law, that acts outside the universe and makes things happen? What is the metaphysics of that? Are there electrons and protons and quarks and neutrinos, and also laws in the fabric of nature, those are laws that apply to them? How come if the laws are part of nature, they can't be acted on? Einstein had a principle that everything that acts has to be acted upon as well. The principle of reciprocity, I think he called it. in the paper on general relativity, how come that doesn't apply to the action of laws on things in the universe? That's really a radical metaphysical idea, the idea of timeless laws acting to make these distributions constant in time. But it's one we're so used to, we don't blink at. So to see how weird that is, let me give you an alternative hypothesis about why nature is stable. And I repeat the same, read the same statement I made before. If we prepare and measure a system we've studied many times, it will be as if the outcome were randomly chosen from the ensemble of past. What if we just cross out the as if the outcome were? The response will be randomly chosen from the ensemble of past instances, full stop. What if nature reproduces itself? Because the governing principle of nature is that nature reproduces itself. Said in this more precise way here, that if you set up a preparation and evolution and measurement of a quantum system that has a lot of precedent, which means that it's been done many times before, there's an ensemble of past outcomes of past instances, and maybe nature just picks randomly one instance from an ensemble of past instances and gives you that outcome now. Maybe that is the law of nature, the so-called law of precedence. That's still a metaphysical idea, but notice it's only about the action of something in the universe and other things in the universe, although through some kind of process of interrogating the past, notice that I need to be able to speak of the past in an objective sense in order to even describe this idea. Do you get the idea? Now, is this testable? I claim yes, in principle. I don't have a precise experiment to propose here, although it's been under discussion with some people in quantum technology laboratories. Why is it testable? Whoops, I don't want to go there yet. It's testable because people are inventing, in the process of attempting to build quantum computers and quantum communication devices. People are constructing quantum states which are sufficiently large and complex, but still quantum mechanically coherent, that it's reasonable to infer that they have no natural precedence, that these are quantum states which have never before existed in the world. And if that's the case, then this principle of precedence should apply, and they should not behave, you should not get the outcome predicted by the Schrodinger equation as you would expect, just applying the laws that have been discovered so far. Now, when I discuss that with people who do real laboratory work, they think it's a joke. And why they think it's a joke is because, of course, when you set up an experiment for the first time, you don't get the answer that you expect. There's a period of convergence. So what's under discussion is whether you can tease out the usual convergence of an experiment to the expected result from the process of gaining precedence and experimentally investigate this idea. Maybe it's going to go somewhere, maybe it's not, but I hope that the possibility of this idea highlights my main points, which are two. One of them is that we increase the empirical content of science by investigating hypotheses by which laws can evolve. Secondly, that naturalism doesn't need to be tied to an idea of timeless laws acting on particles in nature, acting on atoms in the void. Now I'm going to skip cosmological natural selection. I'm going to skip this, which says that the reality of time also allows us to develop new approaches to one of the most vexing questions in physics, which is why so much of microscopic phenomena are irreversible when the fundamental laws are allegedly reversible. But I don't have time to describe it. That's work in progress. So to conclude, the hypothesis of the reality of time offers opportunities for new explanations, to search for new explanations for unresolved foundational problems. The problems of where the laws come from, and what explains the choice of laws, new approaches to the foundation of quantum physics, and new approaches to explaining the arrow of time, among others. If laws evolve, time must be real. Time does not emerge from law, as Julian Barber speculated in that book, The End of Time. Time is what remains when the limits of law are surpassed. As Roberto Unger likes to say, when he, in this sort of throw-out line, time is the change of change. future should not be presumed to be determined. It might be on the present, but not on the arguments which have been normally given for us. So the future might be open. It might be not completely predictable. That depends on what are the processes by which the laws evolve and whether those can be understood as being predictable. So nature may have a genuine element of freedom from determination. And surprising novelty, we can assume, are real things in nature, not illusions. And my main thesis is that this naturalism version 2 leads to a more testable, more scientific, therefore, cosmological theory than attempts to just extend the usual notion of timeless laws to the universe as a whole. To contrast naturalism 1, laws are timeless, immutable, hence inexplicable by means checked by experiment. With naturalism 2, laws evolve in a real physical time by mechanisms presently unknown about which we can make intense falsifiable hypotheses. The claim is that naturalism version 2 has potentially greater explanatory power in spite of, and in fact because of, giving up the hypothesis that laws of nature are absolute and timeless. And I'll stop there. Thank you very much.